Hello to this video. Today we're going to talk about how electricity is generated if we are considering wind, hydro or ocean energy. Here I'm showing you some example photographs. So here we have a hydro plant, here we have a wind turbine, and this down here is a tidal stream generator. What is common between all of these different electricity plants is that they convert energy of motion into electric energy. So for the wind turbine here, we have the wind that is rotating the turbine. For the hydro, we have water flowing down and therefore we get a movement. And for the tidal seed generator here, we have the tide coming in and out, and therefore we get also movement. You can actually see this is a photograph of the tidal seed generator where we have the turbines lifted up, and you can see here where the rotors are. So we have two rotors in this system, which was actually the first large commercial system that was installed in 2008. So for all of these systems, we have energy of motion. The wind is blowing, the water is flowing due to tides or because we have a dam built. And for all of these systems, electricity is generated. So in my part today, I would like to tell you, where does the electricity come from? So how does it happen that we have movement energy and afterwards we have this motion energy converted to electricity? That is, we have the electromotive force, it is called also, so we have induced a voltage. And this we are going to look at today. Okay, so let's look a bit at the history first. And 1820, Ørsted did experiments with a conductor, as we see here, carrying a constant current, and a compass needle. What he found in these experiments is that if there is current flowing, the compass needle is actually orienting itself. And the orientation of the compass needle depends on if you're on this side of the conductor or over here on the other side of the conductor. So if you switch the side of the conductor, what is observed is that the compass needle is turning. And the same if you're going back and forth from behind and in front of the conductor, also the compass needle is turning. So what Ørsted found first of all is that we have, due to the electric current that is flowing, a magnetic effect. And he also investigated then more how strong the magnetic effect is, and saw that overall the effect is such that if you're moving further away from the conductor, the magnetic field is getting weaker, it's stronger towards the conductor. This behavior can be summarized in such a field line plot that we see here for the magnetic field H. So around the conductor we have these field lines here shown in green, and these field lines show the orientation of the magnetic field going around the conductor, and we can see that it's a loop magnetic field around the conductor. So after these experiments, when Ørsted had shown in 1820 that a current generates a magnetic field, Faraday was convinced that also there should be something that is inverse, that is a magnetic field should also induce or generate electricity. So he started doing different experiments to investigate if this is actually happening. And first he actually didn't find much, but then experimenting with this setup here in 1831, he actually saw an effect. So what did Faraday do? Faraday had, first of all, this iron ring that is shown in gray here, and he had two coils. This is coil 1, we have coil 2 here. He again had a compass needle here, so following up on the experiments of Ørsted, he said, well, if there's a magnetic field really inducing a current, that should mean that the magnetic field in the iron ring generates a current in this coil. The current is flowing through the wire here, and we know from the experiments by Ørsted that this current should have an effect on the compass needle. So on the back side, in that sense, he has the Ørsted experiment here where he is checking, is there really electricity generated from the magnetic field that is passing through this coil. And then how he generates the magnetic field is on this side. So he has, well, back then it was not a battery, but he has some energy source here so that he can generate a current flow through this coil. And due to the current flow through the coil, we have, based on Ørsted's experiments, a magnetic field. And then this iron ring is conducting the magnetic field from, or it's guiding the magnetic field from one side, from one coil to the other coil. So the idea was, well, if it is the same as with the electric current generating a magnetic field, then it should be such that if the battery is connected, we have a current flowing through coil 1. This generates a magnetic field, and then this magnetic field will go through coil 2. In coil 2, we will have then, if really magnetic field generates electricity, we will have an electricity in the coil, and then the electricity in the coil should have an effect on this compass needle. So the important point that Faraday wanted to prove is, well, a magnetic field going through the coil here generates electricity. And unfortunately, his experiments first didn't work. And actually, the success he obtained at some point was that he observed in the moment he closes this switch here, so he connects the voltage, he starts the current here. In that moment, he actually observes something with the compass needle. And from this, he then also saw that when he opens this switch here, also in that moment, something is happening on the compass needle. But nothing is happening on the compass needle in between. So when this here has been closed for quite a while, this switch, or also if it's open, nothing is happening, but also if it's closed, the switch, we still have the current flow here. We know there is a magnetic field, but we do not observe anything on this compass needle back here. So what then was the conclusion is that a change in the magnetic field H generates the current. So only in the moment that the switch is being closed or is being opened, so if there's a change in the overall scenario, is something observed here with the compass needle, and therefore that means a change in the magnetic field generates the current I. So really important, a change in the magnetic field. So Ørsted observed for a conductor, we have a magnetic field going around it, following the right-hand rule. Faraday observed for a change in the magnetic field, we have a generated current. We don't have any generated current if there is no change in the magnetic field. So a constant current generates a constant magnetic field, but only a change in the magnetic field generates a current. And so this was really the start of all of it, you could see, of the renewable energies converting mechanical energy into, or motion energy into electrical energy. So let's see why that is, because here in this scenario nothing is moving, but Faraday continued with his experiment, and the next experiment looked as shown here. So in the next experiment, he again had a coil, he again had a compass needle, and from what we were arguing before, so if there's a change in the magnetic field, there should be a current induced, and that should have an effect on the compass needle. And now Faraday went ahead and did the change of the magnetic field such that he used a permanent magnet here, and he moved the permanent magnet into and out of the coil. So he was doing a movement like this, translating the magnet into the coil and out of the coil. And this movement actually then generates, because of the change of the magnetic field in the coil, generates a current, and this can be measured in the simple experiment with a compass needle. So this is the first kind of setup where you get, due to a change of a component, a movement of the component here, so a motion of a component, you get a change in the magnetic field, and this causes an induced electric current. this was the basic experiment, and not much later it was seen, okay, we can also do this a bit differently. Instead of moving a magnet back and forth, we can actually also turn something, so we can do a rotating movement, and this rotating movement can also change the magnetic field through the coil, and therefore also for a rotating movement we can get an induced current or an induced voltage. So this is the first generators realized in that sense. We can have rotating, we can have moving apparatus where we change the magnetic field through a coil, and therefore a voltage or a current is induced, and we get electrical energy that can be used to power applications. And this was all then summarized in Faraday's law of induction. So the mathematical formulation is given here of what we were just observing. So the voltage that is induced, the voltage Ui for the induced voltage, is given by a change in the magnetic field. You can formulate this more generally as shown here. So we have the derivative of the area integral over B, the magnetic field flux density, times the area A, and this surface integral includes the motion effects we were just considering, but it also includes other effects. So let's look at that in more detail. So one scenario would be the B is constant, and then if the B is constant, you could move it in front of the integral, and you see that a change in the area, so a change of the coil, for example, would lead to an induced voltage. You could have a changing magnetic field that is changing over time while the area is constant also. Such a changing magnetic field would, as seen in this induction law here, also induce a voltage. And that is what we just saw with Faraday's experiments. Moving the permanent magnet in and out is changing the magnetic field in the coil, while the coil area itself doesn't change. So the coil is completely fixed, but the magnetic field is changing in this situation. So also in that situation, we can get change in the magnetic field due to movement of a magnet, for example, will induce a voltage. Actually, this law of induction also includes the effect of transformers, because also you can have here no motion at all and just have the magnetic field change over time by, for example, changing the current through a coil. And also this is used in a transformer then, and also there we get an induced voltage. So we can transfer the energy from one coil to another coil, for example. And we will look at that later on more. So Faraday's law of induction here summarizes mathematically all the experimental results that were observed between Ørsted, 1820 around, up to Faraday, 1831, the first experiments into the 1850s. These experiments were conducted and the experimental results were summarized in this equation. So if you have seen this equation before and wondered where does this equation come from, who thought of the equation basically, the answer to this is that this equation is just a very neat, a very nice summary of all the different experimental results. So the charm of this equation is that it has all the different inductive effects included in just one single equation. Of course, you can say the disadvantage is a bit, it has the double integrals here and so on, so it's mathematically a bit more complex, but it has everything included in this one equation. Thanks for watching.